Section 4.4 is on page 379, talks about the mean value theorem. So we have two theorems in this section. One of them is Rolle's theorem. Now we're going to talk about Rolle's theorem and we're not going to use it in this section as much. There's only one problem that we might use it on, and I'm debating that, but let's get it out of the way anyways. This is what it says. Rolle's theorem says if a function is continuous on a closed interval between a and b, and the derivative exists, that's what it means, differentiable on the open interval, and the y values at the endpoints between a and b are equal, then there is a number in that interval where the slope of the tangent is 0. And let me elaborate. If you take this to be f of x, or if you take this to be f of x, or if you take this to be f of x. Of course, it could be this or it could be upside down. It doesn't really matter. What matters is they want at a and b. Did you notice how I graphed those? They want the y values to be the same at the endpoint, right? They want the y values to be the same at the endpoint. And that's why I went back to the same level, because of that case. They say if this is continuous, all those three are continuous and differentiable, they're all derivative exists on all of those, as long as it's a smooth curve. Well, this is what they're saying. They're saying there exists a c. So there's a c in there somewhere, such that the derivative, the slope of the tangent equals 0. At this case, the slope of the tangent at every point is 0. So c could be any of these numbers. That's a special case. If we're talking about this problem, the slope of the tangent equals 0. You could eyeball it. It looks like right there. That's the c they're talking about. And here, if the y values are the same and this is differentiable, again, the slope must be 0. Well, isn't it kind of like right there? The slope of the tangent will be 0 and right there. So here you have two potentials for c and they both work. And that's pretty much what this theorem is saying. Now, mean value theorem is the one we're going to use the most in this section. So let's get that out of the way. And this is what it says. It says, suppose a function is continuous on a closed interval from a to b. That's very important. And f is differentiable. What does that mean? That means the derivative exists on the open interval, so the endpoints don't count. Then there exists at least one c. There's at least one c. So there exists a c in the open interval such that the slope of the tangent equal the slope of the line. Let's say we have a curve, but here the beginning and ending are no longer the same. F of a and f of b don't have to equal. If I draw the slope of the tangent, so if I draw the secant line, wouldn't this be b f of b, and this will be a f of a? Isn't this simply y2 minus y1 over x2 minus x1, which is the slope of that line? They're saying there must be at least one c, at least one, there could be more, in which the slope of the tangent, well, you could eyeball where does that happen. If you go left to right, it seems about that point the slope of the tangent will match. So that's the c they're talking about. And about right there, it seems the slope will match, and that's the c they're looking for. So that's what this is saying. This is the one we're going to use way more than Rolle's theorem. And let's look at how this works. So first, they want to make sure you understand where does the theorem apply and where does it not apply. They say for the following exercises, determine over what interval, if any, does the mean value apply. So how would the mean value apply if f is continuous and f is differentiable? So if I look at this graph right here, I know the sign is continuous everywhere, right? So f is continuous everywhere. How about the derivative? Isn't the derivative of that the cosine of pi x times pi? This is always continuous everywhere. So they're asking over what interval does the mean value apply? It applies everywhere. That's not a problem. How about here? Where would this be defined? Well, let's see. If I take this and I say, where does 4, this is domain now, this is not calculus. Where does 4 minus x squared, where's that bigger than or equal to 0? You have two options. Either you graph this, upside down parabola shifted 4 units, it crosses at -2 and 2, it's bigger than 0 on -2 to 2, right? Or you make a chart, whatever we did in the previous class, right? College algebra, just taught that last semester, and you make the work. Now, so far, this is the limitation. If I take a derivative of this, isn't that 1 over twice the square root of 4 minus x squared times -2x? Wouldn't you say this is not defined when the denominator equals 0? So we can't include the plus or minus because of the derivative, right? So if we say -2 to 2, that will work. Why is that? Because f is continuous on that interval, and the derivative exists as long as you stay away from plus or minus 2. And for that interval, that theorem applies. How about this problem? Again, what's the domain of a log? Well, it's almost the same as an even index radical. You take the quantity, which is called the argument of the log, and set it to be strictly bigger than 0 and solve it. As long as x is bigger than 5/3, this is defined. This is domain. So this is continuous as long on that domain. Now, if I take a derivative, I want to see if it's differentiable. Isn't the derivative of that 1 over 3x minus 5 times 3? And don't you want this to be defined? Isn't this not defined when the denominator equals 0? When x equals 5/3? But that's already included in there. So if I say go from 5/3 to infinity, one, the function is defined, so it's continuous, and second, the derivative exists, which means that guarantees the conditions on the mean value theorem. And now we're going to use it to do the work. Let's see how this works. So this is saying use the mean value theorem. If they gave you this, do you see what the points are? The point is running between 0 and 2. Well, at 0, what do we get? Sine of 0 is 0. And at 2, if I put 2 in there, sine of 2 pi is also 0. So use the mean value theorem, right? What's the mean value theorem? It says f prime of c equal f of b minus f of a divided by b minus a. Find c. Well, if I take a derivative, isn't the derivative of this the cosine of pi x times pi? So that's the derivative. All right. Well, let's see how this is going to play. What is the slope of the secant? That's simply, that's a, that's f of a, and that's b, that's f of b. It's simply y2 minus y1 over x2 minus x1. So, and what's f of c? It's the cosine of pi c times pi. I want to solve that equation. 0 equal pi the cosine of pi c. Divide by pi both sides. So where does the cosine equal 0? Cosine is 0 at pi over 2. Well, pi over 2 is actually, pi over 2 is 1.57, right? And 3 pi over 2. So the answer will be pi over 2 plus pi over 2k. Now let's see how this works. So what equals to that? The angle, I'm sorry. So that's where, so where does the cosine equal 0? That's when the angle, that's when pi c equal, the angle is pi over 2 plus pi k. If I divide by pi both sides, I'll get 1/2 plus k. Well, k equals 0, I'll get c to be 1/2. If I get k equal 1, I'll get 3/2, 1.5, that's in there. If I let k equal 2, I'll get 5/2, that's too big. So two values only. The value of c would be 1/2 and 3/2. All right, how about this problem? The same deal. They're looking at the interval between just 0 and 2. Well, in this case, in 0 and 2. If you plug 0 in, you get 1. And if you plug 2 in, what do you get? You get 4 plus 2, that's 6, you get 7. And here, we want to take a derivative, which is 1 plus 2x, and we want to evaluate that at c, which is 1 plus 2c, and we're going to set that equal, what's the slope of the secant? y2 minus y1 over x2 minus x1. So 1 plus 2c will equal 6 over 2. 1 plus 2c will equal a 3. 2c would equal a 2. C would be 1. And 1 is in that interval. And that's where the slope of the tangent would equal the slope of the secant. Pretty much it's the same work over and over. Let's do that one as well. We're looking at, we're looking at the interval between specifically 0 and 2. So if I plug 0 in, I get negative 1 to the 9th, which is negative 1. If I plug 2 in, 2 minus 1, 1 to the 9th, that's 1. The derivative is actually 9 into x minus 1 to the 8th. F prime of c is 9 into c minus 1 to the 8th, and that equals y2 minus y1 over x2 minus x1. So we're solving, where does 9 into c minus 1 to the 8th equal 2 over 2, which is 1. That is when c minus 1 to the 8th equal 1/9. Take the 8th root of both sides, c minus 1 equal 1 over the 8th root of 8, and add 1 to both sides. C would be 1 plus 1 divided by the 8th root of 9. And that is in that interval. That's 1 point sum. So that's always a guarantee. Let me just shift all the problems. Now we get to the next problem, and they want to go from negative 1 to 1. So here's a problem again. Let's see. They say, for the following exercises, show that there is no c such that this is true. There is no c. Well, let's see. If you plug negative 1 in, don't you get a 1? And if you plug 1 in, you get a 1. And what's the derivative? This is x to the negative 2. So if you take a derivative, that's negative 2x to the negative 3. F prime at c is negative 2 divided by c cubed. And that should equal y2 minus y1 divided by x2 minus x1. That should equal 0 over 2, which is 0. Negative 2 divided by c cubed equaling 0. A fraction equals 0 if the top equals 0. If you cross multiply, you get negative 2 equals 0. No solution. Why is that? Because this function is not continuous at x equals 0. Do you see the domain? And isn't 0 in that interval? So you can't just look at a problem and jump and say, oh, it's going to work. Well, if the two requirements, which were f highlighted in yellow, f must be continuous on the function and differentiable on, f must be continuous on the closed interval and differentiable on the open interval. And that didn't happen here. How about this problem? Okay, forget all of that front stuff. Use a graphing calculator or a calculator. We're not going to graph that. Use a calculator to estimate. We're not going to estimate, but we are going to apply the mean value theorem. So what's f of 0? So I'm looking at the interval. It is 0 to 3. If I put 0 in, I'll get 1 over 1, which is 1. If I put 3 in, 3 plus 2, that's 4. Square root of 4 is, that's 1/2. And what's the derivative? Now, can't I say this is actually, well, I could use the quotient rule, or I could use, say, y is actually, this is x plus 1 to the 1/2. If you move it up, that's x plus 1 to the negative 1/2. So either way, the derivative is bring the power down, subtract 1 from the power. So f prime is negative 1 divided by twice the square root of x plus minus 1 cubed. Now, take f prime at c and set it equal to, which is negative 1 over twice the square root of c plus 1 cubed. Set it equal to y2 minus y1 over x2 minus x1. And what is that? That is negative 1 divided by twice the square root of c plus 1 cubed equaling. This is over 1 over 1. LCD is 2. Or go this way. 1/2 minus 1 is negative 1/2. Negative 1/2 divided by 3 is negative 1 over 6. First, the negatives cancel out. And then, if I cross multiply twice the square root of c plus 1 cubed equals 6, isolate the square root by itself, square root both sides, square both sides, I'm sorry, I did this backwards. Square both sides first to get rid of the square root, cube root both sides, subtract 1, and would that be between 0 and 3? Well, cube root of 9, cube root of 8 is 2. So negative 1 plus a number a bit bigger than 2 is bigger than 1. Yes, that's in there. We found it. You could plug it in the calculator and approximate it if you want, but there's no need. And we have another one to apply in those, and let's see that as well. And here, if we take 1/2, 1/2 plus 1 over 1/2 is 2, that's 2.5, that's 5/2. And if I take 4, 4 plus 1/4, that's 4 and 1/4, that's 17/4. So the slope of the tangent is y, well, let's take the derivative first. Y prime is, this is x plus x to the negative 1. That will be 1. Bring the power down, subtract 1 from the power. Y prime is 1 minus 1 over x squared. So f prime of c is 1 over 1 over c squared. 1 minus 1 over c squared. Now the slope of the tangent is what? So 1 over 1 minus 1 over c squared should equal y2 minus y1 over x2 minus x1. This is a complex fraction. If you make all the denominators a 4, you could ignore all of them. Multiply this by 2, multiply this by 4, and multiply this by 2. You could ignore those denominators. That will be 17 minus 10 divided by 16 minus 2. So I'm looking at 1 minus 1 over c squared equaling 7 divided by, what is that? Is that 8? 16 minus 2, 14. That's a half. Seven over 14 is 1/2. Subtract that from both sides. Negative 1 over c squared equal 1/2 minus 1 is negative 1/2. The negatives cancel out. Cross multiply. And c equal plus or minus the square root of 2. But if I'm looking at the interval between 1/2 and 2, I can't have a negative, so c equals just the square root of 2. That's where the slope of the tangent equals the slope of the secant. And that's pretty much it for this section. This is not a very long section. Now the book doesn't have adequate problems. I gave you 2 problems to apply the mean value theorem on, and we go from there.